Welcome everyone. In this video I'm going to show you my new project. This will be a rather simple but quite useful and powerful project, and I will use this project for some of my future projects as well. And you can also use this as some kind of backbone for many projects which are relevant to this kind of thing. And what you can see here is relatively simple. Here you can see the already built let's call it system, and here are the main components. So let's start with this display. I use this display in many of my projects. This is a simple 128 times 160 pixels 1.8 inch LCD. So it's a simple display, but what is fun about it is that it has an SD card slot. So that means that this guy can be used both as a display to display some sort of information, but it can be also used to read or write an SD card, which you can see here. And then this whole thing is basically powered by this microcontroller. I also use this in many of my projects. This is a STM32F401 CCU6 microcontroller. It costs about the same as an Arduino Nano or Uno, but it's much more powerful. It has many more GPIO pins, and it has many more or much more hardware as well. So for example, it has several SPI ports, several I2C ports, it has native USB, it has much higher clock speed and much more memory and so on. And here actually the fact that this thing can run several SPI ports will be very useful. I will show it when I show you the code. So when we are talking about the project itself, you can see that we have a few wires running from the microcontroller to the display port, which is basically, you can see these connections. Once I can focus on it, there. And another set of wire goes to another set of pins on the microcontroller, because those are the pins for the SD card, as you can see it here on the left side of the board. And one thing what you can see is that then the microcontroller connects to the display by two, let's say, SPI buses. And then what we want to do with this is basically a logger. And what I will do here is that we know that this microcontroller has 10 channels of, or 10 AD converter channels on this side. And we will use all of those 10 channels, and those are 12-bit AD converters, and I will use this as a simple voltage logger here. So what we will do here is that I display all the channels on the display here, and then also log the data on an SD card. And I will show you also in the code presentation how it works and how you can implement your own system. And then you can use this for anything else, that you can log any other kind of data. And then we also have an additional button which is just used for navigation and starting and stopping the logging. And then just one thing which took me quite some time to figure out, that this kind of display cannot work on the same SPI bus both for the display and the SD card. And that's why this microcontroller is very useful, because after some work and after some searching, it turned out that whenever the display is already running and I try to access the SD card, then the code kind of crashes, and then the SD card hijacks the SPI line, and then the display will not be refreshed. So my very quick and dirty solution was that to separate the SPI lines. So then I'm using one bus for just the display part, and another bus just for the SD card part. So that's what we will see here. So I just prepare some things, and we will take a closer look at the display, and I will show you how this thing works. So here is the setup. So I have a multimeter, and then I have a bunch of connections which come from a regulated power supply. So that will feed us some voltage that we will read. And then here we have the display. I inserted an SD card, and then here I just picked the A5 ADC port here, the analog input, and basically that's all. So I just power up this thing, and you can see how it starts. So we have a white display here, and then there will be some information here. It's just a 10-channel voltmeter. And now you see a bunch of garbage on the display here, which is the following. So on the left side you see this column, which is just the channel names, so voltage 1, 2, 3, 4, and so on. And on the right hand side you see the actual voltage in millivolt units. So up here we have something point something millivolts. So the last digit after the decimal point is actually the hundreds of microvolts. And we can almost trust that because we have 3.3 volt reference voltage and 12 bits resolution. And if you divide these two numbers, you will get around 800 microvolts as 1 bit step. So that means that that is our resolution. So we can nearly trust the last digit, which is after the decimal. But the main point here is that we will try to measure some voltages just for fun. So here on the right side we have the multimeter connected to the wires already, and you can see that the V5 channel here is 0 because now I have the pins already wired up, but they are just I just haven't turned on the power supply. And the rest of the pins are showing random values because obviously those are floating pins. So if you leave a pin floating, which you should not obviously if you don't use it, just connect it to the ground. But if they are floating, then they will have different values. So now I turn on the power supply and we will see what is there. So maybe this is more helpful. So we have 2.22 volts here, and if you read the display here, it's 2.14 or 2.12 volts. So it's close enough. And if I change the voltage just a little bit, now we have 186 millivolts, and here we are reading 193.90, so it's kind of close enough. And if I go to a different value, now we have 643.6, and here we have 644.5, so it works. But what is more interesting is that I can use this small button, which is just simply connected to one of the GPIO pins. And if I press it once, then we have a menu here. And we have two buttons, start and stop, which is quite obvious what they mean. And then here we have the units. So the unit is in millivolts. And the SD OK says that the SD card is fine. So we found, or the microcontroller found this SD card. And the file name which we will start logging will be called log_0. And here at the corner you can see a small red square, which also indicates that the logging is not running yet. So now the trick is that I have to press this button for more than 1 second. So then the highlighted button, the start button, will be triggered. We will return to the main display, and then the logging on the SD card will start, and then this small square here should turn green. So let's try that. So now I'm pressing and releasing. So we returned to the main display, and now we are logging all these columns. So actually they will end up as a line. Plus we also log the time. So every refreshing is logged, And when that refreshing happens, we note down the elapsed time, and that's all. And you can also see that there is a green square here. So that indicates that the logging is running. So just for fun, I changed the voltage just to measure something different as well. And we will be able to see that in the file. So here you see it's 1.648 and we have 1.637. So it's like a little bit off. And while this is logging, I can explain that that could be, for example, caused by the fact that since we use the 3.3 volt rail as a reference voltage, I just simply wrote 3.3 volts in the formula that converts the bits into a voltage. But in fact, that 3.3 volt reference is not exactly 3.3. So due to the discrepancy between the real voltage and the defined reference voltage, we can have differences in the readings. And obviously, this multimeter can be off for some other reasons as well. So the truth lies somewhere between these two numbers. I changed the voltage again, just one click up. So 2.6567 watts. And here we have 2.641. So it's off about 10 millivolts. It depends. But you can see that it roughly gives what we want to see and what we should see. And for the sake of the presentation, I grabbed the wire and then I will just pull one of the input pins to ground just to demonstrate that in that case we should receive 0. So I just take the neighboring pin, so let's say A4, and connect it to the ground. And now you see that that is like nearly 0. It's nearly 0 because, as I said, the real voltage is not 3.3000 blah blah blah, but it could be something else. So then if you receive the bits, they might cause some offset. And then I change the voltage again. Let's settle down here. So 1.888, 1.87678. So again, 10-ish millivolts is the difference. And now comes the second trial. So I take the button here, and then I go back to the menu, if I could press this thing. Navigate to the stop button by pressing the button once more. So you see that it became highlighted. And then I just press it long. It should be enough. So now you can see that this became green because now we stopped. And then here we have the small red square. And the log_1 showed up instead of log_0. Because what happens under the hood in the microcontroller is that when we finish one file, we open a new one. So then I could start logging into the new file if I would navigate back. But now what I just do is I press this button once more. I said once more. Then we see some garbage on the screen. And then we return to the original display. So then we can use this as a kind of a voltmeter with 10 channels. But what is more important is that we can use this with the SD card. And that is good because obviously now I'm just using the built-in AD channels, so 10 pins from this row here. But of course you can connect any kind of sensor to the microcontroller. So you can have a thermometer, you can have a pressure sensor, any kind of sensor that you can imagine, and log those values on the SD card and also use this display to display those values. And I will have a future project which I will present to you very soon, which uses the same kind of arrangement, but it will be using a custom designed printed circuit board, and it will use some sensors. But now what we should do is that I should head over to my computer and I should show you the code line by line, which basically runs the display and the logging. So let's look at the Arduino code. And as you could see, this project is based on the STM32F401 microcontroller. So we need to do some preparations. And what is most important is that there are two methods to upload this code, which I will present to you. And one is done with the ST-Link dongle, and the other can be done via USB. And if you use the dongle, then you just have to go to Tools, and when you select the board from the boards manager, which is obviously the STM32F4 series, then in the upload method you have to choose this SWD option. But if you would like to use the USB cable, you have to select the DFU option. And then what you have to do is, when you have the USB connected, then you press down the boot 0 button on the board, and then you keep it pressed down. Then you press and release the reset button, and you wait 2 seconds, and you release the boot 0 button again. And then this will put the microcontroller into DFU mode, so you will be able to upload your code to the microcontroller directly by using a USB cable. But then sometimes the sequence or the timing between these button presses and releases can be difficult. At least I struggled with it. So don't give up after the first time. Typically what you will get is that you will get a notification from Windows that you get an unrecognizable USB device. That means that the microcontroller was not able to enter into DFU mode. So try again. You have it connected by USB, press down the boot 0, press and release the reset button, release the boot 0 again, and do it until you get the proper connection. And that you will see also in the device manager, because you will see a new device, a new USB device, which will be called something like STM32 bootloader or something like that. And then when you see that, or you don't get the error message after doing these button presses, you are in the correct DFU mode of the microcontroller. I just wanted to explain this because there are two easy ways to upload code to the microcontroller. So then here, as you could see, I separated the two SPI buses, and here are the connections. So essentially there is no schematics needed, because you just follow this thing. So for the LCD, you connect the chip select or slave select to the PB12. There is no master in slave out, because the display simply doesn't produce any data which should be sent towards the display. So towards the microcontroller, so we skip that, and then yeah, you can read. So you can read these, how to connect it. But nevertheless, go to my website, and I made the schematics if you want to follow something visual instead of just reading. But this is basically the same, a drawing in a text format. And then we arrive to the code part. So I'm using these two libraries by Adafruit. They are very good. They work with this display perfectly. And then I use the SPI library because of the SPI connections, obviously. And then I use the SDFAT library to take care of the SD card, basically. And then I continue with some pin definitions. So I have the chip select pin for the SD card. And then I have the chip select or slave select pin for the display. And then you can read the comments down here, and you can copy these exactly as I wrote them. And then we want to measure like 10 channels. So I use the 10 available ADC pins, and these are the ADC pins of this specific STM32 microcontroller. And just as a reminder, I also wrote it here that the maximum voltage is 3.3 volts. If you want to use higher voltage, then you should build a voltage divider and divide your input voltage with the corresponding division factor in order to make it compatible with 0 to 3.3 volts. And what we do then with this list of variables, which are the pins, we put them in an array. And why I do this is because when I read these 10 channels, I want to read it in an easy and smart way, and you will see how that looks like. But I want to iterate through all the pins with a for loop. So then I can just use the voltage pins array, this guy here, and iterate through these items of the array, which are the pin variables. So then the for loop will be easily able to loop through everything. And then I do the same kind of exercise with the channel names. So this you could see on the display that on the left side of the display we have V1, V2 and so on until V10, which are just simply the text for the channel names. So of course if you want to have different channel names you can rename these things, but again I use an array and I store these strings in the array because it's easier to iterate through the array with a for loop. And then here I have voltage related variables. So the V out is just the direct conversion of the output voltage, or more specifically input voltage on the ADC pin. And then we have 10 voltages defined in float type. And again, I put these 10 voltage variables into an array so I can iterate through them. And then here comes the more tricky part where I spent some time to figure out everything. So if we look at the board while its USB port is facing upwards, on the right hand side we have all the ADC pins, and on the left hand side we have the rest of the pins, obviously. So on the right hand side actually we also have the SPI1 bus, or SPI1 pins, which we obviously cannot use because now they are used as analog pins. So we have to use the other two SPI pins. And unfortunately, with this display, we cannot share the same SPI bus between the SD card and the display. So I have to use two different and separate SPI pins, and that's what I'm doing here. So I declare this SPI2 and I'm using these pins. You can see it in the description, basically what is what, or you can scroll up and see that, okay, PA15 was the chip select, PB15 was the MOSI, and the PB13 was the SCRK, and PB14 was the MISO or MISO. And then we have the SPI3, and these are the three corresponding pins for that. And we know that the SPI3 is also the one which is used for the SD card. And for that we have to define this SD SPI config, which contains the SD chip select pin and some other parameters, which will make it possible to take care of the SD card. And down here we just create this SD instance, so that SD instance will be used in the future. I use a flag whether we detect an SD card or not. That will be actually a function which is used with this instance called SD, and we use the return value of that function, which will modify the state of this variable. So if we can mount the board, then it will be true. If we cannot, it will be false. File name number. So as you could see in the demonstration, after I stopped the acquisition, the file name changed from log_0 to log_1. And basically what I'm doing in the background, you will see it, this file name number is increased by 1 after I press the stop button. And then here you see the basic idea behind generating a new dynamic file name is that I just write log_, and then I cast the file name number into string and concatenate it together with the log text here, and that will be the SD file name. And obviously I do this dynamically in the code as well. And then this file, SD file, is basically the file that we will be storing and manipulating with this code. And then here we have the TFT So we define it, this object as it is defined in the code. And again, another array. I created this array because I want to have different colors for each line on the display. And I picked those colors which are visible in a good way with the white background. So some of the colors might pop up twice, like the blue that even pops up 3 times, because it's very easy to read on the white display. But you see that they are really separated by several colors, so you will not see 2 blue colored lines next to each other and get confused. And then we have the menu related items. So the item counter is basically just telling us the position of the menu, basically. And then this, yeah, it really tells that which selection is activated in the menu. And if we activated a selection, then the code will know that it should refresh the display and show the user that something is highlighted, for example. And then the next batch of variables is just taking care of the button. So we read the button state into a variable, which is written here. And then we can define a short and a long press time. And that will allow us to have different lengths of time to detect both short and long presses. Yeah, it makes sense. And then the last state keeps track of the last state of the button, because we are constantly polling the button, and then we look at it if it is still pressed or if it's released or if it's not pressed, and based on that we can do further actions, but I will show it how it is implemented. And current state is just that it's the current state, so it makes sense again. And then these are just some timers which are related to the millis in some way, so we can basically, these are storing the actual time or the passed or elapsed time in terms of the millis counter. And then we can again see if the press was long press or short press. And then some other variables, yeah, logging is running true or false. That is because we want to save into the file on the SD card or not, so that we have to take care of and we have to keep track of as well. And then the timer for the voltage updating, which is basically just, again, a variable which stores the millis, and then we count back, for example, 1 second. And if the next reading of the millis is more than 1 second since the previous reading, then we can do another reading from the AD converter. Start time and elapsed time here, it is what they say. So the start time is the millis at the moment when we started the logging, and the elapsed time is basically we read the millis with a certain period, and then the elapsed time is just the elapsed time. And then the new data, it again just keeps track of the AD conversion. So this will be true when all the conversion is finished, so we can be ready for fetching new data again. And then we arrive to the setup. So very important is that we can define a serial, and since this is a native USB microcontroller, like all these STM32 microcontrollers, the number here actually doesn't matter. The throughput of the data will be the same whether you use this number or 9600 or whatever. And then here you can select either you wait for the serial port with this line, I uncommented it or commented it, but yeah, you can do this, or I just keep 3 seconds delay, and then I'm pretty sure that the serial is connected, but yeah, you choose whatever is better for you. And then just a message, just as an indicator. And then I start the 3 and the 2 SPI buses. And then another important thing, this line here. It's not super obvious. When I first put everything together, I was getting very funny readings, and I I was suspecting that something is off with the voltages because I was seeing like a very consistent offset in the readings, but I could not really figure out what was that. It is this. So by default, the analog read resolution is set to 10. So then you will read on a 10-bit resolution scale instead of 12 bits. So 1024 versus 4096. So you can see that there's like a factor of 4 there, and that actually shows up, of course. So when you use this kind of microcontroller and you want to use the highest possible resolution, then you need to call this line, just so you know. Then I put this random blinking of the onboard LED, which is connected to the PC13 pin, just so I see that the microcontroller does what it should do. And then I will initialize the SD card. I will show it how it's done. And then here locally, I just print this welcome screen that you could see. So I just write out, 10 channel voltmeter. It's my nickname for this channel. And then, just the date and the revision number. And then I wait 2 seconds and progress. So I print the first page and then I do one reading just to fill in the full display with the channel names and then the voltage readings, and that's all. And if you remember, we have a button because we have to stop and start the logging somehow. So I have this button pin now connected to the PB6 pin. And I'm using the input pull-up, so the internal pull-up resistor, which means that the default state of the pin or the button will be 1, and therefore you want to pull it down to the ground when you press the button. So the PB6 or other pin that you define has to be connected to the ground through the button. So when you press the button, the PB6 pin will be shorted to the ground, so its state will go from 1 to 0, and that's what we will be looking for when we try to detect key presses. And the option here is very useful because we don't need an external resistor, we don't need extra parts. So if you just want to detect simple button presses, this will do. So you just connect the button to the ground, press the button, short it to the ground, so then the button will be pressed and it will be detected. So then in the loop, we update the selection, which means that the code will look for highlighting if it's necessary or not, and it will do it if it's necessary. We are polling the button. We are reading from the AD converter and update the display. And if it's allowed, we also write to the SD card. So first, let's start with this. So this is a function which has a return value in a float type, and it takes an argument, which is the number of the channel. And this is why I created the actual arrays, because then we can pass the number of the channel here. So channel 1, 2, 3, 4, and so on up to 10. And that will actually be passed here to the analog reads argument. So the microcontroller will know which analog port it should read. And then here we just multiply the return value of the analog read, which can be anything between 0 to 4095. And then we do this calculation. So this is the reference voltage, and this is basically the maximum resolution, or the number of steps from 0 to 4095. And then the return value of this formula is stored in the Vout. And then here I just do some random printing on the serial port just to check the things. And at the end, the function will return with this Vout value, so the reading of a specific channel. So then how we deal with this is that if we are on the first page, and if more than 1 second passed, and obviously you can modify this number. So if I modify it to 500, then it will update every half a second. Then here is my for loop, what I really wanted to explain. So we go from 0 to 10, or 9 to be precise, because it's less than 10. So we iterate over the channels. And what we do is, first I place the cursor to these coordinates. So this is the x coordinate of the cursor, and this formula here is the y coordinate, so the vertical coordinates. And then you can see that if we are in the first iteration, which I equals 0, then this parenthesis becomes 0. So we put the cursor into the 51, x equals 51 and y equals 1 coordinate. And then I print the previous value, which is in the beginning is just empty, with white. So that will kind of in the following iterations erase the previous values. And then I put one of the reading, so in the first case it's the first channel, so I equals 0, put the conversion value, the voltage in millivolts, into this array, and then I put the cursor to the same place where I previously erased the text, and then I select one of the text color from my pre-made array from the beginning, if you remember, and then I print finally the voltage value. And why I need this kind of thing, that I print the previous value to erase the previous value, and then I move back with the cursor and then print a new value, is because if I use two arguments, this set text color can actually get two parameters. It's not written here, but if you go to the documentation, you can actually do this, for example. And that would, if the background color would be also blue, then in each printing, when you refresh the text, the refreshing would look very smooth. But if you want to print different number of digits, it would not work with two arguments. So what I do is a kind of a workaround for this issue. So I think this is a better practice if you have different numbers. And obviously I explained it here why it is a problem. So I print 3 characters first, and they always end up in they start from the same coordinates, this. And then I do a full iteration, so I return to the same field. I want to print a new number. Let's say this number, that will obviously erase it, because it has more characters. But if I would do the other way around, so I print this for, if I print this number first, I have like 6 characters there. And then I print this directly after that. Actually, this won't be erased properly. So then I will see this number on the display, which is obviously wrong. So then when this iteration is done, I reset the timer, which means that the countdown to 1 second or whatever you defined up here will reset, and I let the code know that there is a new data available, and that's that. And then if you want to write this data on the SD card, remember that this is constantly polled in the loop, in the main loop, but the code cannot move forward this line if these are not true. So if the logging is running and there is new data available, so the previous function indicated that we have a new data, then we can enter. So then we open our little file, and if the file exists, so we check it immediately, then we print. And here comes a trick. This library cannot deal with float directly. So what I do, I take a character array, and I know that I will store maximum 6 characters, like here. And then I use this D2strf to convert my elapsed time, so the current reading of the millis minus the start time. And divided by 1000, so it will be expressed in seconds. And then I just convert this, so 6 characters or 6 items, 1, 2, 3, 4, 5, and 6, and then print the float with one decimal number. So for example, it's written here 10.1, and then this conversion of the float will be passed to the time buffer array, and then I print it on the SD card, and then I separate the characters by, or not characters, but the channel values by a comma and a space. Here it's highlighted. So basically the end result will be something like this. So 10, 230. Now I'm just writing random numbers here, but you get the point. So this is the value, which is read or written by or from this time buffer into the file, and then this next line does this here, and then obviously we do it 10 times this because we have 10 voltage values. So, and then the writing of that part comes in this for loop. So we iterate over the stored voltage values. I jump back. We filled up that array, which will be read onto the SD card here. So then, again, the voltage has to be stored in a float format on the SD card, but the SD library cannot deal with float. So first we convert it, same practice or same exercise as up here. So just read the comments. And then we pass the data buffer, and then with a comma we just print all the values. And at the end, when the for loop is finished, so all the 10 values are filled in, we print a line break and close the file. And then we reset the new data to false. So then until the next iteration, when we have all the data ready, we don't do anything. So we have to wait until the new data is ready. And how to initialize an SD card. This was in the setup, if you remember. So here we pass this SD3 config. You see it now in this pop-up window that we pass this to the sd.begin. So then if this is not true, basically that's what the inside of the parentheses means, then we say that the SD card detected is false. So we could not mount the SD card. Otherwise, we could. So yeah, we can progress. And of course, we will use these flags later on when we keep track of the SD card on the display. And then we create an SD file, or at least we try. So actually this could have been moved into this part, because this part only makes sense when we could mount the SD card. So let me do it like this. So if we could mount the SD card, so SD card detected is true, we will try to make a file. So we have a file name. This will be basically the log_0 in the beginning. You see it in the pop-up. And then if the file is available after we created it, then I just print a header. So this will be like the elapsed time and then the voltage 1 to 10. And then I print a line break. So when I start to print the voltage values, then in that case, they will end up in the new line after the header. And then I close the file. So that's that. And now we can see how we can print the first page. So yeah, setting the text size to a larger text size, because we have the larger characters. I erase the previous screen. So if we navigate it from the page number 2 to this, then we erase all the contents, and then we can reprint again. So first we print the channel names. So that's why we created that string array. So this is that string array Hopefully it will pop up. Yeah, you see it, that the channel name here, V1, V2 up to V10. So that will be printed on the left side of the screen. And then I also showed that there is a red or green little square at the bottom right corner of the display, depending on whether we are logging or not, and this is where we draw it. So then if we color the square with green, a 5 by 5 pixel little square, if it's green, the logging is running. That's what you can read from this if condition, and otherwise, so the logging is running equals false, then it's red, obviously. And then if we want to print the second page, which is our menu with the buttons and all, we have a bit bigger buttons, so bigger text is needed. So I set it to number 3, erase the previous, so the first page, and then I start printing the buttons. I just explain one, and then I will just scroll through so you can copy it if it's necessary. But we start with the start button, so the top of the screen. I place it to the x equals 8, y equals 15. So that's the top left corner of the box that we will fill in with the blue color. And then the box will be 112 pixels wide and 26 pixels high, and it will be colored with blue. And then I put the cursor inside the box. X and Y, this is the cursor's position. I set the text color to white, and then I print start in it. And then the same, these numbers, the 4 numbers, are somewhat empirical, so you have to kind of test it, how to write these numbers, like if you want to perfectly place everything. So it takes some time, because each time you need to upload the code to the microcontroller. So yeah, it's not the fastest way, but you can roughly tune these numbers, and then you can do the final iterations quite easily. So stop button again. Fill in the rectangle with blue somewhere below the start, so you can see that the Y is now 45 instead of 15, so it's 30 pixels below the start button. And then place the cursor somewhere, select the text color as white, and print stop in that box. And then I made a different text box, which is smaller, so I changed the text size, and then again it's blue. The cursor is inside the box, the text will be white, and the text itself will be millivolts. So we just tell the user that the unit is millivolts, what we are using to print the voltages. And then we also let the user know if the SD card is detected or not. So again, below this box, there is a other box, which is blue and with a white text. And if the SD card was mounted, I print this SD OK. If it was not mounted, then it's not OK, but it's the same box. So it depends on how we do it. And if we could actually do this, and I separated this just to make more sense, make it more, I don't know, educational, because this could have been in this part. But if the SD card is detected, we also print another box which shows the user the file name, the actual file name, which is used as a log file on the SD card. And if it's not detected, obviously we don't draw anything on the display, because it's not necessary, because we will already see that the SD card is not OK. So we cannot really talk about any kind of file name, because there's no storage to put the file on. So yeah. And then also on the second display, we have to let the user know if the logging is running or not. So we just go to the bottom right corner and print the corresponding small rectangle. And then one of the last parts is that we have to update the selection. So this is how the highlighting works. And then when we press the button we obviously changed this variable to true, and then based on the item counter, so where are we in the menu, we will do something. So if the counter is 0, then we know that we navigated to the first page, so we have to print it. If the number is 1, we navigated to the second page. So what I do here is that I print the second page, and I also highlight the start button, because we actually, when we move to the second page, we are on the start position. So let's highlight it. And then if the case is 2, we are on the second page, but we can only navigate like upwards or forward in a sense that we are still on the second page, because we navigated from the start button here to the stop button. So first I remove the highlighting from the start button, so I just print it again with blue, and then I highlight the stop button, so we will know that the stop button is highlighted. And when one of these cases are fulfilled, we first kind of deactivate this part, so we will not try to redraw any highlighting again, and then this function is done. And then here we check the button. If you remember, this is still a polling function, so this function is located in the main loop. So each iteration of the main loop reads the button pin PB6, and then we check the status. So if there is at least 100 milliseconds elapsed between two button presses, we let the code to do something. So we check these conditions. So if the last state was high, so the button was not pressed, but now it is pressed because now it's low, then we start the timer, kind of start in like quotation marks, that we note down the current reading from the millis, the current return value. Or if the last state was low, so the button was pressed down and the current state is high, so the button was just released, then we note down the millis as the released time. And then we create this press duration variable, which just stores the difference between the released time and the pressed time. And then we decide if the press duration is shorter than the short press time, then obviously we just short pressed the button. And in that case, we are just navigating in the menu. So if we are below 3 with the item counter, we increase the value. But if the item counter wants to become 3, which it cannot do obviously, but that would be in the as branch, instead of making it 3, we make it 0. So then we return to the main page basically. And then we let the code know that, hey, it's time to refresh the display and refresh the highlighting. And if the long press was the interaction by the user, then we have to see where we are standing in the menu. So if we are on the main page, which is the case 0, we have no effect, because if you press the button for a long time on the main display, nothing should happen in my way of implementation. But if we are standing on the second page on the start button, and if the logging was not running, then we start the logging. So we make this true. We note down the start time. We make the item counter 0. So this will put the display back to the main display. And we print the first page. And then we return. So we should just jump out from this part of the code. Or if we were on the stop button, then we disable the logging. Then we increment the value of the file name number, and we already generate the new file name here. So it will be log_1 after the first occasion of pressing the stop button. And then I print the new file name in the text box. So that's I showed you that the log_0 becomes log_1 once I press the stop button. And in that freshly created file, I print the header. So you see time and then the voltage channels, and then I close the file, and I just highlight the stop button so the user will know that, hey, the stop button was pressed. And finally, I just fill in the bottom right small little square with red color, so we will know that there's no logging. And finally, when everything is done inside this big, let's say, code or a bunch of code, then we store the last state. So that is the current state, because that was the most recent reading of the input pin. And then I restart the button time again. So the 100 milliseconds counting starts over. And basically that's that. So this is the code. It's like 600-ish lines, 536. Probably it could be much shorter, but yeah, it is what it is. So I hope that this explanation helped you, and I want to let you know that you should visit my website. Link is in the description, because I wrote a small article about this project, so you can find the schematics, you can find some relevant parts and stuff like that. And I also encourage you that once you visit my website, go to the parts and tools page, because I have all the relevant parts listed there. So if you want to buy the microcontroller, you want to buy a breadboard or the display or any other part which is kind of relevant to my project in some way, you will find it on the parts and tools page. And you can also support me with that. And regarding support, you can also support me by becoming my supporter on Patreon. And I would really appreciate that, because then I can continue making these projects and buying some new parts using that money, so I can improve the content. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.